Hello, my name is Anze. Our group is based at the University of Wisconsin-Madison. Today we will be demonstrating Marius, an easy-to-use system designed to learn embeddings for massive graphs, all on a single machine. Graph embeddings are vector representations of nodes and edges reflecting the structure of the graph, such as information about neighboring nodes. The graph embeddings can be applied to generate valuable insights. For example, the embeddings for a social media graph can be used to perform link predictions such as suggesting a new friend, and those generated for a protein network can be used to predict the functions of unknown proteins. We can create embeddings for knowledge graphs, such as the WordNet 18 dataset. The nodes of this graph are English words and the edges are relations between these words. Here we see a subgraph of WordNet 18, containing neighboring nodes of Scandinavia. Using our embeddings, we can predict gaps in our knowledge base, such as the edge connecting Sweden and Denmark. Learning embeddings for large-scale graphs can be a very resource-intensive task. For example, the Wikidata has about 93 million vertices and 12 billion edges, and for an embedding dimension of 400, it would require 150 GB of storage, far exceeding GPU memory. State-of-the-art graph embedding systems, such as PyTorch Graph from Facebook and DGRK from Amazon, have opted for distributed systems with a large amount of computing resources to handle this problem. This issue can hinder individual researchers who only have access to limited computing resources to apply their models on large graphical datasets. Here we introduce Marius, a system designed for efficient training of graph embeddings on a single machine. Recently introduced at OSDR 2021, Marius can learn embeddings for massive graphs with billions of edges without losing accuracy and with improved speed. It is faster and better utilizes computational resources than comparable existing systems. Marius' beautiful usability, lowering the entry barrier for researchers interested in training embeddings for large graphs. Marius uses simple configuration files to set parameters. All that a user needs to do is to pass in a configuration file to initialize the system. These configuration files allow users to run Marius without ever having to write a line of code. This non-code paradigm dramatically expands the potential user base, allowing researchers with little programming experience to effectively use the system. Here we see a user specifying options in a simple configuration file, and we can run Marius from the command line by just passing the path to our configuration file. Then training process runs and the training embeddings are generated. Marius also features a Python API. Users can write their own custom models in Python and then use them to train embeddings. In this example, we write our custom model TransE by writing our own relation operator translation and our own comparator L2. We then initialize Marius with our own custom model and run the retraining process for a desired number of epochs. The ability to define custom operators and run Marius from Python makes the system extensible and gives the users an easy way to experiment with their own findings. Marius comes equipped with data converters for both input datasets and the output embeddings. Commonly used file formats such as TSV and CSV are supported. Currently, 21 popular datasets can be downloaded by our built-in commands and can be used to test embedding models. Once we have the embeddings trained, Marius can convert them into other usable formats, such as PyTorch tensors. Marius supports large-scale graph analysis. In this example, we show Marius' application over a paleobiology dataset extracted from science documents. This dataset is composed of about 260,000 nodes and 3 million edges. We want to perform link prediction over this knowledge graph to find the hidden edges between different entities, such as the relation between a certain fossil and the geographical location it is collected from. We can perform inference tasks such as link prediction using the trained embeddings. In this example, we generate the top 15 most likely destination nodes connected to the source node Y Fidela through the relation collected from. These results, such as Iowa State and limestone lithology, are accurate and meaningful as they reflect the facts in the knowledge graph. Other results, such as Codell formation, reveal new edges in the graph. These facts were then identified as correct by our domain expert on the basis of a scientific paper that was not in the original corpus. This has been a brief overview of the Marius system and its applications. It is fast, accurate, easy to use, and extensible. Our team at the University of Wisconsin-Madison is continuing to work on improving and expanding the system to tackle even more difficult challenges. Marius is open source now at mariusproject.org. Thank you.